Welcome to an intro to arc length. So the idea here is so far we have focused on the area between two curves. And the volume of the object created by rotating such a region. So that we focused on the area between two curves. That's the wrong two. And the volume of the solid created by rotating that region about an axis. Now we are going to switch to just focusing on a curve. So now we will look at just the curve and we will study its length, which is known as arc length. So we will study the curve's arc length. As well as the surface area of the solid created by rotating the curve about an axis. So instead of rotating a two-dimensional region, we are now just rotating a curve. And so it's just creating kind of the outside of the solid. So we are studying the surface area of the solid formed by rotating the curve about an axis. So we will go ahead and start with just arc length. So starting with arc length, we can approximate the length of a curve by imagining it as little short linear segments. So we can approximate arc length by imagining the curve as short linear segments. Update my screen quickly. So if we draw a picture, we can draw a curve and we essentially are going to break that curve up into a bunch of, let's say, n segments. Of equal size. And then we'll just draw the secant line connecting the two endpoints of each segment. So we're imagining our curve as a bunch of linear segments pieced together. So for each of these curves, we have essentially, we can figure out that length by doing the Pythagorean theorem. So we have our change in x and our change in y for each segment. So the length of each segment, so the length of each segment is given by the square root of delta x squared plus delta y squared. This, however, can be rewritten. So, which can be rewritten as delta x we can pull out front. We are then left with times inside the square root, we will have a 1. Delta x squared inside a square root becomes delta x outside. We will have 1 plus. We would then be left with a delta y over delta x, all things squared. And so essentially, we are looking at a sum, which is a sum of these square root 1 plus delta y over delta x squared. So the delta y over delta x, whole thing is being squared. And then that whole square root is multiplying delta x. So from here, we can get our rule. So if we let delta x go to 0, if we let delta x go to 0, then delta y over delta x, which is just the slope of the secant line, this will just go to the derivative. So delta y over delta x goes to the derivative, right? We essentially go to dy dx, or in this case, f prime of x if f is the function defining our curve. And so what we get then is that our sum becomes an integral and we are looking at the integral from a to b of the square root of 1 plus f prime of x, that f prime of x is then squared, times dx. So essentially, to find the arc length, of f, or of the curve defined by y equals f of x over the interval AB. as long as f is continuous, and differentiable, on AB, we get that the arc length is equal to the definite integral from a to b of the square root of 1 plus f prime of x, that entire f prime of x is then squared, dx. So our overall rule is if f is continuous and differentiable on AB, then the arc length between a and b is the definite integral from a to b of the square root of 1 plus f prime of x squared dx. And the next video, we will go ahead and do an arc length example.